Next up, we have our keynote speaker, Rene Vidal. While we're doing that, Rene is a colleague at Johns Hopkins University in the Department of Biomedical Engineering, and he heads the Mathematical Institute for Data Science there. Rene has been working on problems like this for a very long time and made many contributions, which we're excited to have you here. Thank you for joining us.
Well, let me begin by saying thank you to Charles for a very wonderful introduction, and to the organizers for putting together this really great event. So I want to begin by saying that neural networks have been around for a long time, since the early 1940s. And they've gone through periods of hype where they were thought that they were able to solve a variety of problems in machine intelligence and pattern recognition, to the so-called neural winters, where due to lack of understanding, many people for a good decade would stop working on problems pertaining to neural networks. The reasons for the hype and then decline of deep networks have been various, but one of them has always been the lack of theoretical understanding. The first neural winter followed the development of very simple neurons that were primarily binary, that could be trained with very simple algorithms like add a line. And the main reason for the decline was that it was shown in that paper by Minsky and Papert that they couldn't replicate or approximate XOR circuits. So in a sense, it was sort of an approximation theory kind of issue with neural networks. The second wave of neural networks was based on having multiple layers. There were continuous, new algorithms for training them, like backpropagation, were invented. Convolutional neural networks appeared, and the first successes on recognizing digits were published. And also recurrent neural networks like LSTMs began to be used for speech applications. But again, towards the end of the last century, they were not used anymore. Why? Again, I think partly was lack of understanding. The competition at the moment was support vector machines, and those led to convex problems. We could understand how to optimize them. We could understand how to, why they would generalize. And in contrast, neural networks were black boxes that we didn't have any theoretical properties. So we are currently in the third wave of neural networks, and there is again a lot of hype. They've been incredibly successful in many problems in computer vision, starting in 2012 with a 10% improvement on image classification. But they've also been incredibly successful in speech and in solving some games like the AlphaGo example. But they've already begun to be very successful in the real world. So we see deep learning technology in speech, in automatic supermarkets, or self-driving cars from the big companies. So again, I think it comes to the question as to, well, why is it the case that they're working so well, and whether math can bring some light into the understanding of the performance of deep networks. So around 2014, when we began working, and I was very interested in at the time, Stefan Mallat had really one of the pioneers of trying to use approximation theory and wavelet theory to try to explain the feature learning aspects. One of the aspects that was mentioned as a possible explanation as to why deep networks work better was that the features are learned rather than handcrafted. And this is a comment made in the context that pretty much most of the 2000s, the way in which we did things in computer vision was that we would come up with features that we would extract from the data. Sift, Hog are one of those examples. And we would feed them to a classifier, an SVM typically. And so much of the computer vision research was really coming up with great features because the learning was, it was going to be SVMs. And so what deep learning does is that the features are now learned, and they are learned for a specific application and purpose. And therefore there is this belief that the features that are learned are going to be better for that task. My personal opinion is that what we've done is to replace handcrafted features by handcrafted architectures. because by and large, every single paper that comes out in computer vision, for example, it's a modification to an existing architecture, to adding more layers, batch normalization, to add shortcut connections, make them deeper and whatnot. But the understanding as to why we make those architectural modifications and whether the architectural modifications are derived from first principles is something that is still lacking. The other explanation at the time was that more layers can capture more invariances. And I think it was a great paper, I think, from Stefan Mala about the formation invariance properties of neural networks. But by and large, the idea was that every layer would capture additional invariance, say, to the formation in images. And therefore, by adding more layers, I would capture more invariances. Think, for example, of recognizing the formable objects. You want to be invariance to the formations, translations, and whatnot. So this is an experiment from 2014 showing that indeed, the more layers, the better. And I think this has been replicated even at much larger scale. And it's, of course, much better understood today with the question of over-parameterization. But if you really had to think about what changed, what was different between the 2000s and the 2012, not much really. In terms of the math, the methods, the technology, the architectural modifications of the 2012 networks, the major difference was really data. There was more data, and with more data, you could train bigger networks. And this was possible because you had GPUs to be able to run the backpropagation. And so in terms of real changes and modifications, here's one of them, Dropout. It was a new modification to the way that training was done, where rather than just running your classical stochastic gradient descent, at every iterations, you would only update a random selection of weights. So let's say you select half of your neurons and you zero out their outputs, and then you update the weights only of the remaining neurons. The other modification was the use of rectified linear units. Up until then, the preferred nonlinearity was something like a sigmoid or a hyperbolic tangent. And the explanation as to why rectified linear units are preferable has been pertaining optimization. Basically, if you look at the blue curve, the gradient is nearly zero in most places. And so it's claimed that that causes a vanishing gradient problem, and so you can get stuck. While with a rectified linear unit, that problem is ameliorated because the gradient, at least of the ReLU, is 1 in various places. Of course, if you work in optimization, that answer is not very satisfying, whether the gradient is vanishing or not, regarding guarantees of optimality. Again, compared to support vector machines that are convex, for which you could have guarantees of both optimization and generalization. The question is, well, the problem is non-convex. Why these modifications of using ReLUs would allow me to find better global minima or whatever. So I think back then, when we began doing the first tutorials on the mathematics of deep learning, this was 2015, the state of the art was that the understanding of many of these things was not there. And I think there's been tremendous progress over the last 5 years, but there are still many, many questions that we are very far from understanding. So what are the key questions? One of them is how do we design better architectures? And I already alluded to that right before. The second one is how do we design algorithms that have guaranteed of global optimality? And the last one is how do we ensure that neural networks generalize to new examples? These three questions actually have a very long history as well. The question of architecture design from the perspective of approximation was studied in the late 80s. And this famous result of universal approximation was already there. Basically, what this result says is that if you give me any continuous function on an interval, let's say 0, 1, it can always be approximated within epsilon by a neural network with a single hidden layer. So in particular, little f here is a function, let's say a continuous function in an interval, and capital F is the function that is implemented by the neural network. W and B are the weights of the input layer, and V are the weights of the output layers, and capital N here is the number of neurons. So what this theorem says is that the worst error you can make in approximation is epsilon. So for any epsilon, you can always find a network that will approximate little f within epsilon. So this motivated the question, well, if networks with a single hidden layer can approximate any function, then why do we need deep networks? Shallow is good enough from an approximation theoretic perspective. And so this motivated over the last 5 years, lots of research on better understanding the approximation power and the expressivity of several classes of neural networks. The early papers already showed that there were some so-called exponential gaps in the approximation abilities of deep networks versus shallows. And in particular, there was this paper that showing that really the question is, how many neurons do you need? So yes, you can approximate and you can be within epsilon, but there is the question of how many neurons are needed to achieve that. The second topic is the question of optimization. Again, already in the 80s, there were papers that about this phenomena that linear networks have no spurious local minima, or that all local minima are global in a sense. But many of the other results beyond linear networks were negative results in the 80s. So there were already results that backpropagation fails to converge for nonlinear networks, or would converge only when the data is linearly separable, or otherwise it would get stuck. And we saw some talks earlier this morning on classification with two classes that related a little bit to that. Otherwise, there was the belief that the landscape was just terrible as soon as you added depth. And that was more or less where we ended around the year 2000. And that was one of the reasons, again, why people said, okay, you know, it's non-convex, too complex. Let's just use SVMs. We understand them. We understand why they generalize. Let's forget about this complex problem. So this is an area where there's really been a lot of progress in two primary dimensions. One is better understanding the landscape. And by landscape is, you know, how many local minima, are they global? What about saddle points and things like that? And already there was this paper in 2005 by Benjo about just increase, or what today we would call overparameterized, make the number of neurons go to infinity in that hidden layer, and then you will get a convex problem, and then you can regularize with L1. And so that was already there in 2005. So this notion somehow that by making the networks bigger or wider, the landscape becomes more benign, was already there. And it has been generalized. So there's been papers, and I'll present them in a moment, about this no spurious local minima phenomena. It's also true for deep linear networks and not just for the for shallow networks. I'll be presenting work that extend this no spurious local minima phenomena to nonlinear networks. And in particular, the key that we have observed is this type of nonlinearity known as positively homogeneous. And ReLUs are one example. So we'll be able to generalize these no spurious local minima to nonlinear networks with ReLU nonlinearities. And I think the first plenary this morning already touched also on the connections between statistical physics and the landscape of neural networks. And there's been also a lot of work trying to do those connections to understand better the landscape. The second area within optimization is the question of optimization algorithms. Why is it the case that stochastic gradient descent works so well? What is the effect of noise during training? Can I have guarantees of convergence? Are there implicit regularization properties of these stochastic optimization algorithms? So this is really an active area of research, and there are many papers on this topic. And third, and last but not least, and maybe the most important from a machine learning perspective, is the question of generalization. This is again a question that was studied in the 80s. And at least for linear networks, actually, in the case of linear classifiers, it's well known what is the number of training examples that's needed in order to guarantee that the generalization error is less than epsilon. And by and large, the rule of thumb is that it grows with the number of weights or with the size of your problem. And by and large, say you get some bounds say that they're quadratic. So if you have a network with 1,000 weights, then you should have 1,000 squared training examples, just a rule of thumb. But what happens is that for deep networks, these bounds seem very unrealistic. Like think about ImageNet. It has 1 million training examples, but maybe the networks have 60 million parameters. So you don't have 60 million square training examples. So therefore, people began using other regularization techniques. The idea of early stopping was one. The idea of dropout that I mentioned earlier, just when you're training, randomly throw away half of your neurons and update only half of the weights. Batch normalization is another technique, and all of them have been shown empirically to improve generalization performance. But understanding why this is the case, I think, is an active area of research. So these have been the main initial trends. Initial, I mean, between 2014 to 17 or so. So one of them was that the classical results do not depend on the distribution of the data. So better understanding the input data and using properties of the distribution of the input data to understand the margin of deep networks was the first family of works. The second one was about the implicit properties, implicit regularization of stochastic algorithms, and there's been some talks about that earlier this morning. The third one is the idea that weight decay is not enough, that as you get deeper, you need to use more sophisticated regularizers, and this product of norms of weights emerges as one type of regularizer that has better properties. And I'll be talking about that in a moment, so let me pause on that. But by and large, there's been this idea that we need to rethink about the question of generalization, because by and large, all classical bounds are very far from practical performance. And so where is the cracks and what's happened? So the last 3 years or so have really been pushing three main directions. One of them is, again, the question of implicit regularization. And if I were to connect it back maybe to explain the implicit regularization phenomena with a figure, I think I dropped that figure, so I apologize. So the idea of the implicit regularization really is that the problem is non-convex. You have many global minimizers. Not all of them are equally good. I mean, they're equally good from an optimization perspective, but they're not equally good from a generalization perspective. So how you optimize, what learning rate you choose, the dynamics of learning is going to have an impact on which minima you arrive at, and therefore an impact on the generalization performance. The second approach has been this neural tangent kernel that essentially shows that the learning dynamics is also important, and that if you initialize with small zero weights, there are ways by which you can prevent the weights from moving too much, and in that regime you can approximate the input-output map with a kernel, and therefore you can use classical kernel theory to understand the generalization performance. And the last, and maybe this is the more trendy topic these days, is overparameterization and double descent. The idea is that classical generalization bounds or generalization performance was expected to be as shown here, that the x-axis is say the size of your network or some measure of the complexity of your learning task. The y-axis is your risk, and the dashed line is the training error, and it goes down as you make your network bigger and bigger. But the classical paradigm is that the testing error is going to go down first and then go up. But that paradigm is at odds with current practice, where you make networks bigger and bigger and performance gets better and better. So there was this paper by Michael Belkin, but there's been many others. He will be speaking tomorrow actually about this, on the phenomena that in the classical regime, you observe that the test error goes down and then goes up, but then past the so-called interpolation threshold, where you can perfectly fit the data, it's possible for the testing error to go down. In the more recent papers is really funny. It's not just double descent, you can have triple descent, or you can actually, depending on the bias versus variance trade-off, you can get multiple descent curves. So these three problems, what makes this area very interesting in my view is that they're all interrelated. In particular, some architectures could be easier to optimize rather than others. And in particular, making networks bigger appears to eliminate spurious local minima. So that's one of the potential reasons for success. The other one is that the architecture has strong effects on generalization performance, and the overparameterization phenomena is one. But the third is that optimization can impact generalization. And that's what I already mentioned, that depending on how you initialize your learning rate, you might arrive at a different local minima or global minima with different generalization performance. So is there a way of putting these three together? This is one path, and I don't want to claim, it would be overpretentious of me to claim that it's going to be the successful one. But one way of putting them together that we've been working on for the last several years is the following. One, techniques, some of the stochastic optimization techniques, such as dropout, can be proven to induce automatic regularization. And that regularization that they induced is of the form of a product of weights. And I'll be more specific in a moment. Second, regularization with the product of weights has good generalization properties. And this is the work of Nathan Zerebro a couple of years ago. But third, regularization with the product of weights has good guarantees on the optimization side. In particular, it ensures that there is no spurious local minimum. So as you've seen, one way to unify these three areas is via this product of weights, because if we can put all of these three together, then dropout would automatically induce product of weights that would automatically have both good regularization and optimization properties. And that's what I'll try to give you a glimpse of in the remaining of the talk today. So in particular, I'll begin with a quick summary of optimization for linear networks, just to introduce the notation and review some of the old results. Then I'll go into the landscape for nonlinear networks, particularly trying to highlight the importance of positive homogeneity as a key tool for ensuring global optimality. And third, I'll focus on the analysis of dropout, trying to explain what it does and what type of implicit biases it induces, and particularly the connection with low rank regularization. Just to provide a little bit more detail as to what the results will be, I think this is a picture from the old Baldi and Hornig paper, 1989, on the landscape. And the picture, I think, says it all, that all local minima are global, that other critical points are saddle points. Saddle points are generally strict. This was true for shallow networks. It's not entirely true for deep networks, as we'll see. The second part of the talk will ask the question, what are properties of the architecture and regularizer that make optimization easier? I've already mentioned this question of positive homogeneity as being one of the answers. So this will be the two key results that I'll be overviewing. The first one says that if you have networks that are wide, they have many subnetworks in parallel, and they are all positively homogeneous. So ReLU nonlinearity is going to be one example. Then if you can find a local minimum that has the property that all of the weights of one of those parallel subnetworks are 0, then that is going to be a certificate for global optimality. Moreover, and that's the theorem on the right now, this always happens when the networks are wide enough. And when that's the case, you can always have a local descent strategy that, starting from any initialization, it can find the global minimum. And this is a sort of a landscapes type result. So the algorithm is going to be really a meta algorithm. In fact, even this local descent strategy has many steps that might be NP hard. So it's not that I'm proposing an algorithm to do it. It's really an analysis of the landscape. And the last part will try to answer the following questions about dropout. First of all, is it purely a heuristics, or is it a valid optimization method? And the answer is that it is stochastic gradient descent. But it is stochastic gradient descent applied to a modified objective. So in other words, dropout induces an extra regularization. And so the next question naturally is, what kind of regularization it induces? So the answer is going to be that it induces low rank. So for shallow networks, it tries to minimize the number of neurons in that hidden layer. The third is whether you can characterize the weights and whether dropout induces something on the weights. And so we are going to describe a property called balanced. And so the global optimum networks are going to be balanced when you train them with dropout. All of this, everything I've said so far, it's really limited to shallow networks, linear networks, in fact. So the last part is going to be whether they can be extended to other regularizers like DropBlock, DropConnect, as well as deeper networks. Okay, so with that in mind, let me get started with the technical part of the talk. Linear networks, what is the landscape? So this is a matter of notation. We're going to consider networks with a single hidden layer. X is going to be the input, Y is going to be the output. I'm going to use V to denote the input weights and U to denote the output weights. And the reason for putting the transpose there is, as we're going to see in a moment, is really very well connected with matrix factorization. And the dimensions are going to be N0 for the number of inputs, and 1 for the hidden layer, and then 2 for the number of outputs. And so therefore, the hypothesis space is really the set of maps from the input X to the output Y, parameterized as the product of these two matrices UV transpose. And the reason for the transpose is just so that U and V have the same number of columns. And the number of columns is the number of hidden neurons, okay? So if you think about a matrix factorization, again, think about the number of columns of U is the number of neurons here. So this is the risk or the loss that you want to minimize. So it's the expected square loss. And the interesting thing is that this can be expressed in terms of the covariances of the input. So sigma YY is the expected value of YY transpose, and similarly the covariance of X and Y and the covariance of X and X. Okay. Now, this was already well known. Actually, this is all from the 1989 paper by Baldi and Hornick. And trivial statements you can make immediately. If the number of hidden neurons is larger than the input and output dimensions, then the UV matrix is really can be full rank. So you might as well just forget about the fact that you have a network and optimize over the product directly. Moreover, this is a quadratic problem in that case. It's going to be strictly convex if the sigma X matrix, if the covariance of the input data is full rank. And so in fact, it can be solved in closed form. And so the entire input-output map is given by this formula. This is just essentially like linear regression. So that was already, is a note actually, just as a warm-up, in fact, to motivate that the over-parameterized case there is simple, and that invertibility or richness of the input data allows you to get a closed form solution. The other important note is that once this matrix is invertible, you can convert it always into a matrix factorization problem. So you can essentially forget about fully supervised learning and just think about it as a linear algebra matrix factorization style problem. All you need to do is pre-multiply by the inverse covariance, which is sort of whitening your input data if you wish. But this was the result from Baldi and Hornig. It says that if the covariance of the data of the input data is invertible, but also this matrix sigma, which, as you can see, depends on the input-output covariance matrices. If both of them are invertible, then the set of global minimizers of the objective, actually, this is now in the case where the number of hidden neurons is less than the number of inputs and number of outputs, because if it is more, I already told you, you can compute everything in closed form. So assume now that N1 is small. So in that case, the U matrix is really just the top eigenvector. So the Q matrix here is the top N1 eigenvectors of that sigma matrix. So the bottom line is the input-output covariance matrices, the eigenvectors of it, essentially, already tell you what the U is, the output weights, and similarly for the V weights, okay? And the input-output map of the network is exactly what you would have obtained in the overparameterized case, but projected onto the top N1 components, if you wish, of this input-output covariance. So again, this is not the only global minimum. There is an entire family of global minimizers, because you can always make a change of basis here. You can always multiply U on the right by something, and similarly for V. So this was 1989. The results have been relaxed and extended in various ways. So the assumptions of invertibility have been eliminated in recent work, but they've also been extended to deep networks. So in the case of deep networks, the notation is the same. The input is X, the output is Y. We're going to have W1 through WL is going to be the weights, and N0 through NL are going to be the dimensions of the input-output. And in the case of linear networks, this is the input-output map. You simply have a chain of linear transformations, W1, W2, WL, being applied to X to produce the output. So same story as before, you can write down the risk. Now the risk is a function of the network weights. And as before, it can be expressed in terms of this trace. And the very funny thing is that nothing changes at all. You can substitute the product of all your matrices by a single matrix, and you get the same risk as in the Horny and Baldi paper from 1989. And therefore, if the dimensions of your intermediate layers is sufficiently large relative to the input and output, then you can immediately get the entire map of the network in closed form without having to even learn the intermediate weights. So again, the only interesting case is the case where the intermediate dimensions are a little bit smaller than the input-output dimensions. And that's exactly what this 2016 paper from Kawauchi does. Again, if the covariance matrices are full rank, and this input-output covariance matrix sigma is also full rank, then the following results are true. So any local minimum is global. Other critical points are saddle points. And if this matrix that it's in the middle, that is the product of a subset of the weights, is full rank in a sense, then the saddle points are going to be strict. In the particular case where you only have one hidden layer, so L is equal to 2, then this is true. And so therefore you always have strict saddle points. And that was the result that was already known for shallow networks. But this paper also shows that as you have deeper networks, the saddles might not be strict. So in summary, there's been great work in the case of linear networks. The landscape is well understood and is relatively simple. And as I said, all local minima are global, was known. and other critical points are saddle points, and they might be strict or not, depending on the depth of the network. So let me now move to the case of nonlinear networks. What happens if we add nonlinearity? So, and this is the work here at the bottom, and the result is going to be that there is no spurious local minima, and that this can be achieved if you properly regularize, and you need to add regularization to the picture. Everything I've said so far, there was no regularization added. So the statement of the theorems at a high level is that you assume that the networks are homogeneous and have parallel structure. You assume that the regularizers are homogeneous, and these will lead to sufficient conditions for global optimality. I'll present the conditions in the case of deep and very large networks, but it's from a pedagogical perspective is way easier to introduce them within the matrix factorization setting. So I'll do that first, because I've already convinced you that matrix factorization is a particular case of training neural networks. So my view is, in fact, that neural networks are like matrix factorization, but with nonlinearities added in between. Okay, so how are we going to extend these to networks with nonlinearity? The key is going to be to connect non-convex problems to convex ones. How? This is, for example, a non-convex function on the network weights, U and V. What we're going to be constructing is a global lower bound. The global lower bound is going to be a function of a different variable, x. In fact, x is going to be the input-output map, if you wish. In the case of matrix factorization, it's just going to be UV transpose. And this is mathematically what I mean. Capital F of x is going to be a global lower bound for f of uv over all uv matrices whose product is equal to x. But the lower bound is going to be tight in the sense that the global minima agree. The minimum over x of 1 versus the minimum over u and v subject to uv transpose is equal to x are going to be the same. Okay. How do I do that construction? So here's how we do it. So on the left, maybe let me begin on the right. The problem on the right is very much like a neural network training problem. You give me a matrix of labels, y, and I try to factorize it into the product of UV transpose. I already explained that, why that shows up. And I have some laws. The square laws could be one example. And then we are going to see what regularizers we use, but for the time being, I'm going to add some regularization on U and V. How can we construct a convex problem associated with this? Well, we are going to substitute UV transpose by X, and that's what you see here on the left. And then I need to be somewhat smart, and it's maybe non-trivial at the moment, but somehow I need to go from some regularizer in UV to some regularizer on X, which is what's here. And so if the problem on the left is such that the loss is convex on the second argument, which typically is because square losses, cross entropy, all of those are convex on the output. If the regularizer on the output is convex, then the problem on the left is going to be convex. But the problem on the right is not. So the question comes as to how do we construct the, what is theta? What theta is going to be allowable? How do we do it? So I'll begin with the other way around, in fact. Let's suppose that I had a regularizer on the left. And let's suppose that it is a low rank regularizer, such as the nuclear norm, which is nothing but the sum of the singular vectors of that matrix, as illustrated here. And so the sum of the singular vectors of that matrix can be written in terms of the product in a very fancy way, and that's the so-called variational form of the nuclear norm, where on the far right, you begin with the matrix X, you factorize it in terms of UV, any factorization, and it might not be unique, there might be many of them. And among all possible UV factorizations, you choose the one that minimizes this regularizer. What is this regularizer? is the sum from 1 to r. R here is the number of columns of u sub I, which is the ith column of u, and v sub I here is the ith column of v. So remember in the introduction, I was advocating this idea of sums of products of weights. That's exactly what's showing up here. This is the sum from 1 to the number of hidden neurons of u sub I here is the output weights of the ith neuron. V sub I is the input weights of the ith neuron. So this is really a regularizer that is summing over the hidden neurons the products of the norms of the weights. Okay. And the magic is that if you minimize that with respect to all possible weights u and v that produce the same output x, that induces a norm on the output. And the norm is actually the nuclear norm, which is a low rank regularizer. So that's what we're going to do. We're going to choose the sum of products of weights as our regularizer, and that will induce a nuclear norm on the product. Now you may say, well, this is maybe very restrictive. Can I do something more sophisticated? And so the answer is yes. So this comes from a paper from Francis Back. You can choose any norm on the U weights, any norm on the V weights, and the same result is true. It induces a norm on the output. And this will be relevant in many applications, in fact, because there are many applications where U might be your dictionary and V might be your coefficients, or it might be a space and time decomposition. And so you might want to use sparse penalties or something else other than L2. So there is plenty of flexibility as to what norms you can impose. The only thing that matters is that in the end, no matter what regularizer you put in your weights, it induces a convex regularizer on the output. That's the main message. So with that in mind, now I can state the first theorem that essentially says that provides a characterization for what local minima are global. So what this theorem says is that if the loss function is convex on the second argument and one's differentiable, then if you have a local minimum, uv, for the weights, such that one column of u and one column of v is 0. In other words, if this was a neural network training problem, is if you find a local minimum for your neural network training problem, such that all of the weights of one neuron are 0, okay? Then those weights are the global minimum. That's essentially what this says. But moreover, if you now take that global minimum on the UV space and you take the product of them, that gives a global minimum for the convex problem, where you are actually optimizing in functional space. You're optimizing directly on the input-output as opposed to optimizing on the weights. So this theorem really illustrates the picture that I had put here at the beginning. That's exactly that. There is a global lower bound, and it is convex, and the global minima agree. And that's now stated formally with this theorem here. And at the end of the day, what this theorem is really a question of capacity. If the global minimum is low rank and you overparameterize your UV by making it bigger than it should, you can reduce the loss. Sorry, you can reduce the regularizer, if you wish, by setting some columns of U and V to be 0. And so that's sort of at an intuitive level what this theorem says. The second theorem is whether you can actually find it, at least conceptually, and how. And so the picture that illustrates this for the second theorem, there are two aspects to it. One is, or maybe a key one, is that we need to optimize over the number of hidden neurons. And so you might ask, what happens if the number of hidden neurons is smaller than that of the global minimum or larger? So if it is smaller, this is the situation. If this network size is not big enough, you might indeed have a local minimum, and this is what the blue curve illustrates. So what we're going to be doing is, if you find a local minimum, then let's see if we can escape. How are we going to escape? We're going to escape by augmenting the network size, by adding an extra neuron, or in the matrix factorization case, adding an extra column to my factorization. So if I do that, this is exactly the question that I'm asking here. I am at a local minimum. Let me add a second dimension. Is it possible to go down if I augment my optimization problem with that extra variable? And if the answer is yes, I will take that descent direction in the augmented space. Up until eventually, I'll be in a situation that by adding more neurons, I won't be able to further decrease the objective, and that's when I stop. Conversely, if I start with a network that is larger, then I will stop immediately because I can set to 0 some of the network weights without the possibility to further decrease the objective. So more formally, this is the statement of the theorem here, that if the number of columns is large enough, local descent strategy can reach the global minimum from any initialization. And so again, this happens with a finite size. That's another property that you will be able to do. Increase, for example, if you start with a small number of columns, what you're going to do is that you increase one column at a time, and eventually one column will be 0, and that's when you stop. Okay, so how do we extend these results now to deep networks? Everything I've said so far really looked like matrix factorization. There was no nonlinearity. So how do we extend it? So in the case of deep networks, we begin with input data X, we apply a linear transformation, and then we apply a nonlinear activation. And we repeat this process for the second layer, and we repeat this process multiple times. So from a notation perspective, this capital phi is going to denote the input-output map of the network. It's a function of the input X, but it's also a function of the weights. Since I'm concerned primarily with the training problem, I am going to think of phi just as a function of the weights from now on, okay? So in matrix factorization, what was the key property? Really, the key property was twofold. One, the input-output map is just the matrix product. And interestingly, it can be decomposed as the sum from 1 to the number of columns of UI VI transpose. Notice that this is a map that is homogeneous. It's a map that is of degree 2. If you scale the columns of U by alpha, if you scale the columns of V by alpha, you get alpha squared. So this is a map that is of degree 2. So in trying to generalize matrix multiplication to deep networks, what we're going to do is what is written here at the bottom. Give me any map little phi that you want, like that rank 1 outer product of the weights. So W sub I here is the weights of the ith subnetwork. The supra index here is the layer. So this is take the ith subnetwork and take the input output map of the ith subnetwork. That's what the little phi is. And then just sum them up. So in picture, and that's what's illustrated here at the top left, you have multiple networks that you put in parallel. All subnetworks have the same architecture, but they can have different weights. And then you add them up. So this is one of the assumptions of our theorems, that the networks need to have parallel structure. And so networks with a single hidden layer is one example. But here, this could be a very complex example, many subnetworks in parallel. So this was the theorem in the case of matrix factorization. You begin on the far right with the output Z, and you write it as the product of the matrix of weights. And there are many weights that produce that same output. And among all possible U's and V's that give rise to that output, you search for the ones that minimize the sum of the product of weights. How do we extend this to deep networks? How can we construct something like the nuclear norm for deep networks? So here's the construction. Begin on the far right with Z that denotes now the output of the network. The output of the network is therefore phi, which is the input-output map, phi of the weights. Phi of the weights gives you that output. There are many weights, many W1s through WK that produce the same Z. Among all of them, choose one that minimizes a regularization function that also decomposes from the sum from 1 to R. So each subnetwork has its own regularizer. And this is parameterized here by a little theta. Okay. The key property that is needed is that this little theta needs to be homogeneous as well. So in the case of matrix factorization, this was homogeneous of degree 2. In the case of deep networks, this can be homogeneous of a higher degree. The key property here is that this function is convex, and the function as a function of the output. So this is exactly the generalization I was talking about. You can begin with any deep nonlinear network as long as it's homogeneous, any regularizer as long as it's homogeneous, and the minimum of the regularizer with respect to all weights that produce the same output, Z, is a function of Z, and it is a convex function of Z. And that is the key intuition, that you build a regularizer for the network that effectively is tightly connected to a convex function. So with that, this is the main result of Ben's work, which is that if you have a loss function as before, that is convex on the second argument and once differentiable, then a local minimum of the neural network training problem that minimizes the loss plus lambda times a regularizer. If you have a local minimum such that for one of the subnetworks, all of the weights are identically 0, then that gives you a global minimum for the original training problem. And even more, if you take those globally optimal weights and produce the output of the network, they are going to give you the global minimum for the convex problem of just minimizing directly with respect to the output of the network. And so this convex problem is again the loss that compares the labels Y to the output of the network Z, plus this super fancy regularizer on Z, which is maybe complex, maybe difficult to compute, but I know that it's convex. So that's why I know that this problem is convex. And this construction is true for matrix factorization, and in fact gives rise to the nuclear norm, but it's true also for many tensor factorization problems, because all tensor products are also homogeneous of the degree of the tensor. So you can do tensor factorization with a suitable regularizer of the degree of the tensor, and this framework applies to tensor factorization as well as this type of the networks. As soon as the input-output map and the regularizer is positively homogeneous, these results apply. So let me skip the second theorem. It's really of the same flavor, but again, the same result, that as the size of the network becomes larger enough, gradient descent, or not gradient descent, a local descent strategy can find the global minimum from any initialization. So in summary, the summary of this optimization part of the talk is that you can have a lot of guarantees for global optimality. And by and large, they depend on the size. The bigger the network, the more benign the landscape. The theory here guarantees global optimality when the size of the network is measured either as the number of neurons in a hidden layer or the number of parallel subnetworks, but new results are needed for more complex notion of size. The notion of depth has not been studied here in this work. The second aspect is that to achieve these results, for linear networks, you don't need regularization, but as soon as you have nonlinearities, having regularization is important, and ensuring that these regularizers are positively homogeneous of the same degree as the network is also important. and that these regularizers, in a sense, control the number of parallel subnetworks. Now, I didn't touch on any optimization or convergence here, and in fact, some of the meta algorithm for computing is NP-hard. So studying subclasses of regularizers that allow the optimization to be more tractable is important. Let me just stop here and skip the last part of the talk. Let me just finish with shameless advertising of the Institute. Primarily, we are hiring. The deadline is December 1st. So all of those of you who are interested in the foundations of data science, please apply to Johns Hopkins. Thank you.
Thank you so much for that. That was amazing. We'd like to start by opening up with questions from the Q&A. The first question is there a general, parentheses, exact rule or function to calculate the number of training samples needed for your network?
I don't think so. I think that, I mean, this question is the question of generalization, is well studied for linear classifiers, is somewhat studied for kernel methods. But for deep networks, I don't think we have a clear answer as of yet. So I don't think I can offer anything meaningful there.
Thank you. I believe that Lenka has a question. Would you like to unmute and ask?
Yeah, sure. Thank you, Rene. I was wondering about the results on the global minimizers. It could be that even global minima generalize badly. So how do we ensure that this is not the case?
It could be the case that global minima generalize better or local minima?
Badly, that global minima generalizes badly. Like the paper that I was citing at the beginning of my talk is precisely showing that there are many global minimizers and some of them generalize well and some of them generalize badly.
Yes, so the two answers to the question. The first is simply to say that the entire talk was primarily about the landscape and understanding local versus global minima without connections to generalization yet. Two, you're totally right. And I think I said it briefly, not all global minima are good. And the key question is, why is it the case that some simple algorithms or some simple regularization tricks happen to find global minima that have good generalization properties? And I think there are a few examples where that has been done. The implicit bias, for example, for linear networks trained with, in the connections of that with margin, are a few examples where those analyses have been done. The analysis of the neural tangent kernel is a few other examples, but I think it's still an area where we don't have very definite answers. It could be the case, and maybe this is wrong, but it could be the case, maybe a local minima generalizes better than another global minima. I think the hope has always been that one of the global minimizers would be the one with the best generalization properties. But the understanding of that, as far as I know, is still very limited.
Tommaso Poggio has a follow-up question. Existing deep nets without regularization generalize well. How do you explain this?
I think a key point of the talk was that you think, actually no, maybe I did not get to that point of the talk. Actually, I skipped the last part. Maybe I'll try to jump to one slide of what I was going to say at some point. This was trying to explain dropout, and I completely skipped it. But I think there is a little bit of a misconception in my view. In practice, when we are doing the optimization, we do a lot of tricks. We do dropout. We do stochastic gradient descent. We do batch normalization. And we think we are training a loss that is completely unregularized when we do that. This paper focuses on understanding dropout in particular and shows that as soon as you make a modification to the optimization algorithm, such as introducing dropout, the loss that dropout minimizes, even though you think it is an unregularized, you begin with your standard square loss as shown here. The loss that the stochastic algorithm is minimizing is a modified loss, which is equal to the unregularized plus a regularizer. So in fact, this expression here on the right, theta, is the probability of retaining neurons. And so when theta is 1, which means you retain everything, then you have no regularization. But as soon as theta is smaller than 1, you are augmenting your loss with an extra objective. So the answer, I think, is that many of the things that are being done are introducing regularization, and they are successful because of the regularization that is being introduced. It's just that we don't know what it is, and this is an example for which it can be analyzed.
Thank you. And one last question while we still have time. From Francesco, do you think the generalization can ever be addressed without a generative model?
I don't know. A priori, I would say I don't think so. I think by definition, generalization is a statistical question of the comparison between the expected loss versus the empirical loss. And the expectation is an expectation over the input-output data, and you have to have a generative model to do that. I do think actually that there is a strong and tight connection between the distribution of the data and the architecture that is done for solving that particular task. And that generalization comes from that right interplay. So I would find it very difficult that it could be done without having a generative model, but this is just speculative.
Thanks. Do you have time for one more question?
Yes.
All right, so the last question in the Q&A. Can you briefly highlight what kinds of insights can be or are expected to be obtained by analyzing linear networks towards deep neural networks with nonlinearities?
I think it's important to acknowledge the fact that there is a gap between linear and nonlinear networks that is big. And I think spending too much time exclusively on linear networks is not a good idea in the long term, because there are many phenomena that occur in nonlinear networks that is not present in the linear case. I think the global optimality for linear networks is I think is a good example to know and to have in mind, to understand how linearity simplifies things a lot in the landscape. But I think that the fact that many, or at least a popular nonlinearity is ReLUs, and that a lot of examples of networks that are working well have this property of homogeneity, I think it establishes a good connection with what happens in the linear network setting. But I would tend to agree that in moving forward, we should reduce the percentage of research on the linear networks and move more into the nonlinear one, because that's where the interesting new phenomena is happening.
Great, thank you so much. Thanks again, Rene, and thank you all our speakers for the second session.